Today, we'll be solving LeetCode 146, LRU Cache. This problem is all about designing a data structure that works like a least recently used cache. That means, whenever our cache reaches its maximum capacity and we need to add a new item, we remove the least recently used item from it. Least recently used simply means the one we have not accessed or updated in the longest time. The problem gives us two main operations. The first is get, which takes a key and returns its value if it exists in the cache, otherwise it returns -1. The second is put, which takes a key and a value, updates it if it already exists, and if not, adds it. If the cache is already at capacity, we remove the least recently used item before adding the new one. The important challenge here is that both get and put must run in O of 1 average time complexity. That means we can't loop through the cache to find items, everything needs to be instant lookups. So how can we achieve that? The perfect choice here is a combination of two data structures, a hashmap and a doubly linked list. Here's why. The hashmap lets us look up keys instantly in O of 1 time. The doubly linked list allows us to maintain the order of usage, the most recently used items should be near the front, and the least recently used ones should be at the back. When we access an item or update it, we can move it to the front of the list instantly, and when we need to evict an item, we remove the one from the back. Now let's walk through the code step by step so you understand exactly how it works. We first create a node class. This is a helper class to store each key and value pair, along with pointers to its previous and next nodes in the linked list. Next, we define our LRU Cache class. In the init method, we take the capacity, store it, create an empty hashmap, and then set up two dummy nodes called left and right. The left node represents the least recently used end, and the right node represents the most recently used end. We connect them so that left's next is right and right's previous is left. These dummy nodes make adding and removing real nodes simpler because we always have neighbors to work with. We also define two helper functions inside the class. The first is remove node, which disconnects a given node from the list by linking its previous node to its next node and its next node back to its previous node. This works in O of 1 time because we have direct pointers. The second is insert node, which always adds a node right before the right dummy node, meaning it becomes the most recently used. We connect the nodes previous to right's previous, and the nodes next to right, and then update the neighboring nodes to point to this new node. Now, the get method takes a key. If the key exists in our hashmap, we first remove that node from its current position in the linked list, then insert it at the most recently used position by calling our insert helper. Finally, we return the node's value. If the key is not found, we simply return -1. The put method takes a key and value. If the key already exists in the cache, we remove it first from the linked list so we can update its position. Then we create a new node with the key and value, store it in the hashmap, and insert it at the most recently used position. If adding this new node makes the cache size exceed capacity, we remove the least recently used node, which is the one right after the left dummy, and also delete it from the hashmap. This design ensures both get and put run in O of 1 average time complexity, because hashmap lookups, inserts, and deletes are O of 1, and doubly linked list insertions and removals are also O of 1. The space complexity is O of capacity, since we store at most capacity number of nodes in the cache and hashmap. And that's how you solve LeetCode 146. Thank you for watching and let's keep learning.